Okay. Hi, everyone. It's my honor to be here to present Song Linke's work, The Road to Trust, Building Enclaves within Confidential VMs. And this is a joint work of Institute of Information Engineering, Chinese Academy and Science, and Ant Group, and Indiana University. The first, the TE is designed to isolate code and data of confidential workloads for other software on the system. TE ensures security by restricting access to sensitive computations. The trust execution environment. For example, Intel XGX follows a strict workflow to create and manage enclaves. This ensures the sensitive data remain protected. And the other hand, AMD SEV is also a kind of TE. It provides a different approach by encrypting the entire virtual machine. So the TE has branched to two different families. The first one is process-based. For example, Intel SGX, and another branch is VM-based, for example, AMD SEV, TDX, or ARM-CCA. And nowadays, VM-based TE are more prevalent now. But they introduce a new security concerns. That is, what if the guest OS might be compromised in VM-based TEs? This is a critical concern arises when the guest OS in the VM-based TE is compromised. How can users still establish trust in applications running within a confidential VM? Address this challenge is the core motivation of Song Linke's work. If we trust the application, for example, the enclave running on the guest OS, then the whole lifecycle of enclaves should be trusted. The previous work, such as VSGX, attempt to address this issue using a 2 VM mode. And separating untrusted application from the enclave. However, as VSGX treat a whole VM as the TCB, the amount of the TCM is too massive, and it has great TCB, and it has significant overhead for word switching. So here comes our solution, the nested SGX. It adopts a similar thread model to the VSGX. As the guest OS is untrusted, we built the only trusted component, the enclave, on the top of the guest OS. However, it's not enough. Now we will talk about nested SGX targets. The first goal is how to mitigate the significant overhead of the word switching without compromising security requirements. The second question is nested SGX built on CVM sufficiently compatible? Can it support a certain level of application ecosystem? So here is our contribution. The first, nested SGX minimize reliance on the guest OS and builds trust by making the enclave the only trusted component. Secondly, nested SGX is compatible with SGX. Nested SGX has similar management of enclaves to Intel SGX, so it significantly reduces the effort required to port existing application of SGX. And the third, we implemented nested SGX on commercial hardware, the evaluation shows the overhead is comparable of that of SGX, affirming its efficiency and viability. Nested SGX utilize AMD SEV SNP's virtual machine privilege levels, also as we know is a VMPL. After enabling VMPL feature, VMPLs from VMPL 0 to VMPL 3 separate the permission and the privilege on VMPL level can have on the memory page. Every VMPL shares the same address space with VMPL 0 representing the highest privilege level and the VMPL 3 representing the lowest. In the nested SGX, we separate the privilege. The trusted component will be in the VMPL 0, while the untrusted part is in VMPL 1 level. The security monitor will run in the kernel mode of the VMPL 0, managing the enclave running in the user mode of VMPL 0. While VMPL 1 hosts the guest OS application, this privilege separation ensures that the enclaves remains secure even if the guest OS is compromised. Our architecture of the nested SGX has 3 key features. The first one is security monitor and memory isolation and integrity of enclaves. The security monitor manages the enclave lifecycle. In the security monitor, we implement SGX instruction emulation layer, which enables the monitor to better manage enclaves. First, the application will send a request by our control syscall to the driver in the guest OS. The driver in the guest OS will switch the VMPL level to the monitor. The security monitor will then finish the initialization and the measurement of enclaves. Secondly, for the synchronized entry and exit to the enclave, after the control flow has trapped into the monitor, the security monitor will use sysreturn instruction to enter the right position within enclave. After the computation is done in the enclave will use syscall to go back to the monitor. After that, the monitor will switch the VMPL to go back to the guest OS driver. Thirdly, when a synchronized exit, also known as AEX, happens, the exception raised by the enclave will handled by a security monitor. The monitor will store the context of the enclave and switch back to VMPL 1. Then the subsequent resume instruction comes. The security monitor will load the context for the enclave and use the iReturn instruction to resume the enclave component to process. Lastly, when we want to delete the enclave, the monitor will clear and recycle enclave pages after receiving the request from the application. Okay. The second key feature of nested SGX is memory isolation. The isolation is established since the booting process of nested SGX. At the booting process, security monitor initializes the guest OS and sets up its page table. It then hands over control to BIOS of guest OS. And therefore, the page the guest OS can access is in the control of the security monitor. Besides, the EPC of enclaves are allocated and managed by security monitors. The monitor records the state of the EPC by using EPCM data structure and handles the page faults and the enclaves. Moreover, the monitor also provides shadow page table for the enclaves and the application. While the page table of application is managed by the host by the OS, and the page table of the enclaves is managed by security monitor. The security monitor can maintain same GVA to GPA mapping for data sharing. by depriving the VMPL1 guest OS the privilege to execute the page content, the security monitor can share the data between enclaves and applications smoothly. Lastly, the isolation of enclaves are guaranteed by the VMPL feature, since the guest OS can't access secure memory in VMPL 0, including enclaves. On the other hand, since the memory of enclaves are managed by security monitors, the monitor also ensures the page table of enclaves does not map to any GPAs of security monitor and guest OS, which strengthens isolation between those components. The third feature of the nested SGX is a measurement and integrated track of enclave. The root of trust starts at AMD root CA, which will guarantee the trust of the CVM. The security monitor of nested SGX will generate AIK. The ultimate attestation report will include some customized privacy generated from nested SGX. Now, here comes our security analysis. The untrusted app guest OS, including nested SGX driver, is running at VMPL1, which is untrusted, since the security monitor and the enclave use separate page table from untrusted world. This isolation guarantees the untrusted world can't do harm to the security monitor. The nested SGX driver is tasked with switching VMPL. Another consideration is what if the host VMM is untrusted. So the untrusted VMM can only observe the eCall, OCall, AX patterns, which also exists in Intel SGX. So no additional attack vendors are introduced by the nested SGX. So besides, what if the enclaves itself is untrusted? This is easy to understand since the security monitor controls its page table, and every syscall related steps enclaves can take will not bypass the security monitor. And lastly, also the chain of the trust. Okay. Now comes to implementation. Our nested SGX is of 7,500 line of code. It's based on open source Linux secure VM service module framework, and we deploy it on our AMD server. As for the evaluation, we compare our system with Intel SGX hardware and the simulation mode of Intel SGX on the same machine of our nested SGX. We used several macro benchmarks, also did some real-world evaluation using real applications. And the result shows that it's much quicker than VSGX, while the Rust implementation of cryptographic is a little bit slower. We also measure the latency of the nested SGX. And here is the N-bench result, the SSL, IO performance, and the SQLite, and also TLS servers. All these are application evaluation. So the limitation of our works can be listed as here. Not all SGX model feature are supported, and the scheduling of enclave the thread is lacking, and also applications written without SDK are not supported by our work. Now here is the conclusion. We present a new a new architecture named Nested SGX. It is a hybrid of VM-based and process-based TE models. It builds trust enclaves within confidential VMs, and we also present a more compatible and secure and efficient CVM framework. Okay, thank you. By the way, due to some visa problem, the Song Ling Ke is not here today. So if you have some more questions, you just be free to contact him by email. Thank you.